AI Podcast. I'm Michael, and today we're unpacking a new ACL 2025 paper called ToolHop. In one line, ToolHop is a benchmark that checks whether language models can break a complex question into steps, call several tools in sequence, and recover when a call goes wrong. Even top models still miss a lot, so there's clear room to improve.
Hi, I'm Elena. Great, start me at the finish line. What's the headline finding here?
The take-home is simple. When tool use is required, the leading model lands around 49% accuracy. Tools help compared with answering directly, but multi-step tool-driven reasoning remains tough.
Got it. Who's behind the work?
It's led by Junjie with collaborators from Fudan University and ByteDance. The corresponding authors are Tao Gui, Qi Zhang, and Xuanjing Huang at Fudan.
Thanks. Now give me the lay of the land. What problem are they trying to solve?
In real tasks, you rarely ask one question and stop. You decompose it, hop through several subtasks, and use different tools along the way. The field has lacked a benchmark that really pressures models to do that in a grounded, verifiable way. Earlier efforts often tested single-step calls or judged the process with another model, which can introduce bias.
So the gap was an evaluation that's truly multi-hop and checkable end-to-end.
Exactly. ToolHop tries to fill that hole. It gives models complex queries that genuinely require multiple tool calls, and it makes those tools locally executable so results and error messages are reproducible.
Walk me through how they built it.
They start from real multi-hop questions and expand each into a small ecosystem of tools. Think of 3 stages. First, tool creation. For each sub-question, define a tool with a clear name, description, and parameters. Second, document refinement. Enrich the specs so tools look more like what you'd meet in production, with structured parameters rather than just strings. Third, code generation. Turn each tool spec into working Python functions with error handling and clear feedback when a call is malformed. The dataset ends up with just under 1,000 multi-hop queries and a few thousand tools.
That locally executable bit sounds important.
It is. Because the tools run locally, the benchmark can verify final answers automatically and surface concrete error messages when a call fails. That's crucial for diagnosing where a model went wrong.
How do they test the models?
They evaluate 14 language models across 5 families under 3 scenarios. First, direct answering without tools. Second, a mandatory tool use setting where you have to use the tools. Third, a free choice setting where tools are available but optional. They score answer correctness, and in the mandatory setting, they also track invocation errors, such as calling a tool that doesn't exist, inventing parameters, or omitting required ones.
Nice and practical. What happens when you run the models?
Tools help. On average, moving from direct answering to required tool use brings a noticeable bump. Still, even the best model tops out in the high 40s, which tells us there's substantial headroom.
So the glass is half full and half empty.
That's a fair way to put it. The authors also tease out family-specific behaviors. Quen models tend to fire off several tools in parallel, which can backfire when the task needs sequential handoffs and careful parameter use. Claude models show strong direct reasoning and sometimes recover from tool errors using internal knowledge. GPT models benefit a lot from detailed tool feedback, and when you strip feedback down to minimal hints, their correction rate drops. In general, larger variants handle tool use better.
Any surprises about underperformers?
Some families look weaker in tool-heavy settings because of interface limits. If a model can't combine natural language outputs with well-structured function calls or can't express certain parameter types, it struggles on multi-hop tasks.
Before we wrap the results, say a word about the data itself. How big is this benchmark, and how real does it feel?
Each query typically needs 3 to 7 tools, and the queries span a wide range of domains, not just trivia. The tool specs push beyond toy strings toward arrays, booleans, and objects, and every tool returns explicit errors when you misuse it. It's not the messy web, but it's realistic enough to stress planning, handoffs, and recovery.
Let's put a critical lens on it. What should listeners keep in mind?
3 things. First, because the tools are local and deterministic, reproducibility is strong, but real-world APIs bring rate limits, latency, and authentication, so external validity is the next step. Second, the team used a top model to assist parts of the construction, which is efficient, but may leave stylistic fingerprints in tool docs or code. Third, comparisons across open and closed systems always depend on the function calling interface. The paper normalizes a lot of that, but it's hard to eliminate completely.
Do the authors acknowledge any limitations?
Yes. They stress that ToolHop is an evaluation resource rather than a training recipe. There isn't an immediate strategy bundled to improve multi-hop tool use, though the same pipeline could be adapted to create training data.
Okay, bring us home. How should practitioners use this?
As a sanity check, if your product relies on multi-step tool use, ToolHop will tell you whether your model handles decomposition, sequencing, and error recovery, and the diagnostics help you see whether you're over-parallelizing, missing parameters, or ignoring feedback.
And where should research go next?
A few directions stand out. Train with curricula that reward correct call sequences and penalize hallucinated tools or parameters. Control parallel calls so you don't get ahead of intermediate results. And design feedback that's detailed enough to steer recovery without hand-holding. Longer term, add live APIs with realistic failures to test robustness under pressure.
That's clear and useful. Thanks, Michael.
Thank you, Elena. This is AI Podcast, and that was ToolHop. What it tells us about where tool-using language models stand today and where they need to go next.